Hi, I hope everybody's doing well today. All right, learning targets. I can distinguish between and identify physical and chemical properties. I can distinguish between and identify physical and chemical changes. I can explain how the three states of matter, solid, liquid, and gas, differ from one another at the molecular level. So this one might be a little bit different than, say, eighth grade physical science, using the characteristics of each state. I can utilize a heating curve or cooling curve to determine if a phase change is endo or exothermic. These words, endo and exothermic, might be a little new to you as well. So a couple new things, couple review things in here, but some really good graphics, just saying. So definitely take a look at those as we go. All right, chemistry is the study of the composition, the structure, and the transformation of matter. That's what we're looking at here when we're talking about chemistry. Okay, so looking at these different components here, composition, structure, transformation. All right, now physical changes. Physical changes starting up here. No change in chemical composition, same substance, and they tend to be reversible. So let's take a look here. Like blending and mixing, that's a really good example. And then you just usually use a separation technique to separate the different components. You can, there's various ones you can do in order to do that. Bending, sculpting, yes, like lots of metals can be shaped and formed and things like that. That would also fall under the physical change category. Shredding and tearing, just going into smaller pieces. What we're noting here is that there's no change in the chemical composition. It's still the same substance. It's just being broken down into smaller pieces. Boiling, evaporating, and melting. Now, this is the hardest one, I think, for physical changes that people get confused. Because say like you have ice, which is H2O, and then you melt it into water, which is still H2O. So the phase changes are always going to be physical. They're never going to be chemical. Still the same substance. It's really just about overcoming the forces holding them together or reforming those forces as they're shifting phases. Sublimation is a type of phase change. I'm not sure that you're familiar with this one, but this is where you go from a solid directly to a gas. Wonderful example that you'll see in soon, probably for Halloween. People like to put out the dry ice and it sublimes at like normal room temperature, and you get to see the nice smoky deal there. The opposite of sublimation is deposition. Now, of course, that's gas directly to solid. There's not many wonderful examples of this, but you can think of like the icing on planes when they're up in the clouds up there, like it goes directly from gas straight to ice onto the wings of the plane sometimes. Alrighty, states of matter. Now these GIFs are just great. So pay attention to the movement of the particles as well as like, the spacing of the particles. So this is how we're talking about on the molecular level, looking at these particulate model diagrams. So looking here for the solid, you see they're very close together. They're like vibrating in place. They don't have a whole lot of movement. So let's talk about a solid here real quick. Not as easily compressed. They have limited free space, so they're not very compressible. They're rigid and they do not flow easily. And they have a fixed shape and volume. Okay, so when we're looking at states of matter, you also want to look at not just the spacing, but actual movement too, because all particles have kinetic energy. They all have some movement energy, even solids. Now, the only time a particle would ever stop moving and have no kinetic energy at all would be at absolute zero, which is 0 Kelvin. And that's when there's nothing. That's negative 273 degrees Celsius, by the way. That would be when particles stop moving. So as you can see, even solids are going to have a little bit of vibrational energy there, vibrational movement, which is, kinetic energy as well. They're looking at the liquid. As you can see, they're spaced together, but they have more movement they're closer together, but they're moving around. They have more free movement. They can flip and rotate and do other things than just vibrate in place. Not easily compressed too because they're really close together. They flow easily, pour easily. They can slide past each other. and they assume the shape of their container. So we would say that they have an indefinite shape, but they have a definite volume. So indefinite shape, a fixed volume, but not a fixed shape, basically, is what we're going for there. Now, the last GIF over here is showing you your gas. Okay, gases are in the constant random motion. They're hitting the walls of their container. And it's showing you going from the red where they're cooling it down back over here to the blue while they're trying to heat it up. So the blue one is cooler. The particles aren't moving as fast. You give it some heat, temperature goes up. They move a lot faster. They have more kinetic energy. Now, gases, of course, can be compressed because they have lots of spaces between the particles. They do flow easily. And what we say about gases is they take the shape of the container completely, okay? The entire volume of the container. So it fills the container completely. We would say it does not have a shape or a volume, indefinite shape, indefinite volume, because it takes that, it assumes the entire shape of the container. And the particles are very fast in constant random motion, bouncing off the walls of the container. All right. Good pictures there. All right, so looking at the heating and cooling curve, which you'll have to be able to examine these and know what's going on. I don't know if you've ever seen one of these before. Has anybody ever seen a heating or cooling curve? Yes, no? All right, good. Okay. So heating would be going this direction where you're adding energy. Of course, cooling would be going this direction. Cooling curves are very similar. They just are the opposite. They start up top, they go downward and so forth. So this would be your gas, this would be your liquid, this would be your solid. The cooling curve is just going the opposite direction. Now the plateaus you should notice are the phase changes. We have freezing, melting, condensing, boiling, and in chemistry we call this vaporizing. Oops. Vaporizing, okay. As you can see up the cooling curve here. Now looking at this little GIF here, which you can play, by the way, that's why this is so large. You can actually see, you know, what's happening here, going down. The gas is cooling, and then eventually it's going to hit that boiling, that condensing point, which is the same as the boiling point number, and then it's going to start condensing into a liquid, and then eventually it becomes a liquid, and so forth. Now, the kinetic energy, okay, of the molecules as a solid, the kinetic energy here is going to be very much lower than the others where they're just vibrating in place. The liquid has a little bit more free movement, so the kinetic energy would be increased at this point. And then the gas, of course, particles have the most kinetic energy because they're in constant random motion. So as you can see, that kind of goes through the different phase changes on this is the cooling curve going the opposite direction where they're cooling it down. Another perspective here, looking at this particular one, which I like because it shows the particles at the top and they're kind of in their movement as well. So the solid here, you know, they're all together, but once they hit this melting point, it starts to melt, okay? You'll see that some of the particles have broken free and other of the particles are still together. So this particular look of the particles is about halfway, where you have like half solid, half liquid now. When you get all the way over to this point is when you're going to have all liquid at that point. And then the liquid will start warming and they'll start moving faster and faster and gaining kinetic energy until they get to this point, which would be the boiling point, and they start vaporizing. And as you can see right here too, you have like half gas particles up here, half liquid particles here. You're about there in terms of the middle of it vaporizing into gas. Now, in order for it to vaporize or melt or anything, it has to overcome something called intermolecular forces. We abbreviate them IMFs. So the particles aren't just, you know, they're randomly sitting. The solid particles have pretty strong IMFs holding them together. That's why there's limited space and they have that definite shape and definite volume. So the stronger forces holding them together. Now, in order to get it to melt, to allow them to spread apart a little bit, it has to overcome some of the intermolecular forces to do that. That requires energy, okay? And if you require energy, it's called endothermic. So your phase changes of melting and vaporizing and also sublimation All of those are endothermic processes because it requires energy to overcome the forces. Okay. Now, when you're going the opposite direction, like for condensing and freezing or depositing, any of those processes where the forces are going to reform, those are called exothermic because when you form a force or a bond, you release energy in that process. So releasing energy, or the energy's leaving or exiting, that is going to be called endothermic. So I like to think of exo as exiting, like leaving the system. Endo, you have to input the energy, absorb the energy. Exo, it leaves the system and goes to the surroundings. And always, if you're overcoming forces or bonds, it requires energy. You have to absorb energy to do that. If they're reforming the forces or you're forming bonds, those processes release energy, so they're going to be exothermic here. Also looking at the example of hydrogen bonds. Let me erase some of this. Okay, this nice little GIF here showing hydrogen bonds, and I'm sure you've heard of hydrogen bonds from last year in bio because they talk about it. Hydrogen bonds are the specific type of intermolecular force that holds water molecules together. There are different types of IMFs, but hydrogen bonds is a specialized one, and water obviously does this. So as you can see, it's slowing down as it's cooling and eventually establishing more of these forces here, okay? And slowing down the particles eventually to be locked in its like it's a hexagonal shape for the ice. That's why it expands as it freezes. So just a specific example showing you that for water. All right, chemical changes. So let's take a look at the chemical changes. Chemical composition changes, new substances form, they tend to be one way. So if we're looking at this particular example, you have hydrogen plus oxygen giving you water. So if you're looking here, the hydrogen bond, or the hydrogens have to split their covalent bond there. The oxygens have to split their covalent bond, and then they have to form a bond in order to make the water happen, okay? So that GIF is showing you the H's break up, the O's break up, and then the H's and O's form bonds in that process. So you go from two substances into a new substance. Over here, this is also a molecular view. This happens to be CH2O right here, and the other one is like HCl. So as you can see, the HCl breaks apart. The H attaches over here to this O, which is the red ball, and the chlorine, which is in green here, attaches to the carbon. So it forms a new compound in that process. But bond breaking, bond forming, that's a chemical change. You're getting a new substance out of it. So let's take a look at some examples here, like burning, cooking. Chemical changes, the composition changes, new substances forms tends to be one way. You can't really reverse this. The logs and the wood become ashes. You also have gases being given off in burning. Cooking, obviously, as you can see, the egg would not go back to its original state. Rusting, corrosion, oxidation, tarnishing, okay? This is what oxidation really is, the reaction where it's reacting with oxygen and air to form the rusts, and different metals have different colors of rusts. The rust that you think of when you think of rust is the reddish kind, reddish brown kind, but like the Statue of Liberty is made of copper and it has like a green rusty color. That is going to be, you know, what it forms, that copper oxide on the outside. But that's one other form. You actually have it reacting with oxygen and air and it forms metal oxides. Decomposition, rotting, decaying, spoiling, any of that, of course, is going to be the bacteria is breaking it down into different particles and making new compounds out of it. So these are buzzwords for recognizing chemical changes. Indicators of chemical change or reaction. First one is an energy change. You have two options here. Like you could lose heat, like a cold pack where it feels like it's getting colder. You like break the cold pack and it ends up starting to get cold. And then of course fireworks is an example where it's like where it's giving off heat, okay? That would be losing, actually, this is the one that's losing heat because it's giving off heat to the surroundings as it's exploding. The cold packs are taking in the heat from the surroundings. That's why it feels cold to us. Just a quick little lesson about heat transfer. You put your hand on, you know, say the chalkboard or the whiteboard, and it feels cold to you. The reason why it feels cold to your hand is because your hand is transferring heat to the whiteboard. So your hand is losing heat, the board is gaining heat. So in that particular case, the board absorbing the heat would be endothermic. Okay, and then like your hand releasing the heat would be exothermic. Another example of a chemical indicator of chemical reaction, light produced, as you can see right here, and we're going to show you a couple of examples of that happens. You burn magnesium or any of these ones for the fireworks where you get the colors, the bright lights. That's also an example of the light being produced in the process as well as giving off the heat. Another example, a gas forming. I'm sure you've put vinegar and baking soda together before, and as you can see, it likes to bubble out. That means gases are being produced. Specifically, carbon dioxide is being produced there. Another example is a solid precipitate forming. You might not have heard of this word before because it's a more sophisticated chemistry word. But basically, I have two solutions here of different mixtures. One of them has potassium iodide in it. The other one has lead nitrate in it. Okay. Don't worry, you don't have to name those, but they're both clear solutions. But when you put them together, a reaction occurs and you form lead iodide. Lead iodide is this yellow solid stuff that falls to the bottom. And that's what we call a precipitate. Falls out of solution, precipitates to the bottom. Now that is an indicator because you're going to get new substance there. Also, the fact that it was two clear liquids to begin with, it looked like two clear solutions, and it produced this bright yellow. That color change also gives you an indication of chemical reaction. All right, endo and exo. Let's look at those. Exothermic changes. Oops, went too fast there. Hold on, back. Exothermic changes, of course, like I said, heat leaves, exits, goes to the surroundings, okay? Giving off heat, it gets warm if it's a chemical reaction. Endothermic, heat is absorbed by the chemical reaction, and then it's going to feel cold to us because the heat's being removed from us and being put into the system. Now, this is in terms of chemical changes and chemical reactions. You want to think about endo and exo in terms of the phase changes. Just remember which ones you have to add heat to, absorb heat, like melting, vaporizing, and subliming. Those ones you have to add energy to. It has to absorb it. Those ones are all endothermic, and then the opposite direction, those guys, the reforming of the forces, those are all exothermic. So condensing, freezing, and depositing, those ones are all exothermic. All right, nice little flow chart here. Ask yourself the question, are these properties determined without changing the identity of the substance? If your answer is yes, you're going to be over here on the physical properties category. If it is no, you'll be over here on the chemicals property side of things, okay? The identity remains the same, it's physical. If the identity changes because you get a new substance, it would be chemical. Does the property depend on the amount of the substance? Yes, it does. No, it doesn't. Let's look at what that means. If it does depend on the amount of the substance, we're talking about an extensive physical property. Mass, volume, length, and shape. Okay, those ones, electrical charge, okay, depends on the amount of the substance there, okay? Like I have 10 grams of water or I have, 100,000 grams of water. Of course, that would be a difference in volume and mass and other things like that. But on the intensive physical property side, color, boiling point, melting point, density, these kind of things, doesn't matter if I have a sample that's 30 grams or if I have a sample that's 500 grams. The boiling point of water is always 100 degrees Celsius. So it doesn't matter if it's a small amount or a large amount, that property is amount independent, I would say. Some of these other ones here, like ductility too, can it be formed into wires? Malleability, those are for metals. Can you pound it into shapes and sheets and things? Specific heat, we're going to get to in more detail, but that's how much heat is needed per gram per degree Celsius to raise the temperature. Boiling point, that's phase change. Melting points, phase change. Color, yeah, like the substance is just blue. Doesn't matter if I have 50 grams of it or 500, it's blue. That's not going to change by amount. So these are some of the ones that you want to think of when you think of intensive physical properties. Extensive ones are due to the amount dependent. All right, so here looking, we have intensive properties: luster, hardness, color, boiling point, volume, mass, size, weight, and length would fall under extensive. So just a nice way to sum it up on a little chart here. Looking at the chemical properties. How does the substance react in the presence of? Now, it could be any of these things. It could be water, air, heat, an acid, a base, another element. Does it react? If a spark, is it flammable? These kind of things are what we're talking about over here. Now, I do want to throw in that there is an extensive chemical property in terms of the heat giving off. Okay, so like for instance, if we're burning a log itself versus burning a twig, the log, of course, is amount dependent. It's going to burn more, it's going to produce more heat than, say, the twig in the process of the burning, which would fall under more of the chemical. So heat, the amount of heat that can be produced is extensive chemical property there. So here, toxicity too is another one. We think about that in terms of like poisons, how it reacts in our body. Oxidation would be more of the rusting, corroding idea. Heat of combustion, how much heat per mole, per gram. Chemical stability, flammability, I'm sure like alcohols and gasoline and other things like oils and stuff are flammable. You don't really have to worry about coordination number. That's more of an AP thing, definitely more complicated. But reactivity is important. Possible chemical bonds. It has to be able to rearrange and form bonds in order to be able to react with one another. And enthalpy of formation, that's also like a heat thing where it's a certain amount of heat that's either released or gained when you're forming compounds. All right, so let's practice here. We're going to look at certain examples from different perspectives. First thing here, we want to look and see if we have a physical or chemical change. And if it's a physical chemical change, is it endo or exo? In this example too, we're going to look for any physical or chemical properties and then decide if they are extensive or intensive. Okay? So gallium is a lustrous metal with a melting point of 29.8 degrees Celsius. It can melt in the palm of your hand. If you're at you're outside and it's 87 degrees, it will melt in your hand like showing here in the picture. So what does anybody see a physical or chemical change happening here? Let's look at that part first. Yes, it's physical. Why physical? What's the word here? Definitely physical. Changing state. Yeah, you have melting right here. Come on, pen. Oh, hold on. Went forward. Back. Come on. Melting. Okay, good. It's changing state. Now, melting, is that endo or exo? It requires energy. It absorbs energy to overcome the forces. Yes, to break apart. Very good. Endo. Now let's look at the property part. Anybody see a description of a property over here in what we're talking about? Do we have a physical or chemical property being talked about? What's this thing right here? The melting point. It's an actual temperature at which gallium is going to melt. Is that a physical or chemical property? It is physical. Good. Is it extensive or intensive? Yeah, it is amount independent. It does not matter the amount. We could have this amount on the hand, or we could have, you know, a big, huge box of it. But if it got to, 85.6 degrees Fahrenheit, it would start melting. Doesn't matter. Very good. So that's how we would label this particular example. So we have the physical change and we have the physical property here. This one is, we said it was endo, and we said it was intensive, not exo, not exo. Okay. Let's look at the next one. All right. What's being expressed here in terms of the leaves changing colors? We're really only going to look at this one from a physical or chemical change standpoint. Leaves changing colors in the autumn. Is that a physical or chemical change? Anybody know? Yeah, it's chemical. Good, very good. Now the really hard part. Is it endo or exo? Think about the fall. Think about what happens in the fall. Yeah, very good. Okay, temperature dropping. It's getting cooler. Then the leaves are that signal to start changing. That processing and that temperature change in releasing energy there. All right, this one. This is a fun one. Everybody likes to grill, right? Okay, so using a propane gas grill, it's going to burn in the presence of oxygen, forming carbon dioxide and water vapor, and heat in the process. So here is the particle model. Here is the balanced reaction: propane, oxygen, carbon dioxide, water, and then heat. Okay, so physical or chemical here? Definitely chemical. Very good. Good. Now, is it endo or exo? Yeah, it's definitely warming up. We're feeling the heat. The heat is exiting the system. All right, to us in the surroundings. We're feeling it from the surrounding standpoint. Good, good, good. Now, is this a physical or chemical property? This burning here, is that physical or chemical? Yeah, definitely chemical. Very good, very good. See that a lot of people are getting this. Now, is it intensive or extensive? Does it matter the amount? Does it not? It is, if we have a gallon of propane versus, say, 2 gallons of propane, which one's going to burn or produce more heat? Yeah, the more amount. So this one, in this particular case, if you have more of it, you're going to produce more heat. So definitely going to be extensive there. All right, so let's take a look at this one. This one, we're really just focusing on the properties and looking at it from this example, because we're just giving you data about the substance, not anything that's happening to the substance. So the density of the cast gray iron engine block is greater than the aluminum alloy engine block. Are these physical or chemical properties here? Looking over here. Physical, good. Now, of our physical properties here, we have density, we have volume, we have weight. Any of those intensive, where the amount does not matter? Very good. Density is mass per unit volume. So it doesn't matter if you have a ton of it or not, the density should remain the same. So density would be the intensive. Okay, so this would be the intensive I. What about volume? Is that intensive or extensive? Yes, it is extensive. It does matter on how much you have. If you have more of it, you're going to have a larger volume. You have less of it, less volume. So what do you think about the weight or the mass in kilograms? Also extensive. Very good. Yes, because more you have of it, the more it's going to weigh. Very good. All right, let's take a look at this one. This we get to look at it from both perspectives here. Is this a physical or chemical change? We have a metal was added to an acid, bubble formed, and the container became warm. Definitely chemical. Good. Now, is this endo or exothermic? Yes, it says warm here, so we can assume that heat is leaving the system and we're feeling the warmth. There you go. Now, is this a chemical or physical property? It is a chemical property. Very good, because we're reacting with an acid. Now, is it amount dependent or amount independent? Is the metal going to react with the acid depending on more of it or not more of it? Independent. Good. I would say this is intensive. So the metal is going to react with the acid or the metal is not going to react with the acid. It doesn't really matter the amount. Certain metals, well, there's a lot of metals that react with like hydrochloric acid. In this case, we have zinc over here. That's the metal. It's showing you zinc and hydrochloric acid. There are some metals that do not react with hydrochloric acid. There's a few that aren't, but there's plenty of them that do. So if it has the capability of doing it, it really doesn't matter the amount. It is an intensive chemical property.